Welcome back, and this is the last in the series of videos looking at the alkanes. In this video we're going to be looking in particular at the mechanism. Mechanisms are very important in organic chemistry. They show us how one functional group can be converted into a different functional group. So you're going to need your notes, and we're on page 23. So this is the reactions of alkanes with chlorine or bromine to produce a halogenate alkane. In the presence of UV light, that's ultraviolet light, the alkanes can react with chlorine in what we call a substitution reaction. A substitution reaction is where an atom or group of atoms are replaced by a different atom or group of atoms. This is technically a free radical substitution mechanism. So the overall equation for this is we have our methane reacting with chlorine to make chloromethane and hydrogen chloride. So we can have ethane, CH3CH3 reacting with bromine to form one bromoethane. So one of the hydrogens has been substituted for by a bromine atom, and we also get some hydrogen bromide gas coming off. But because of the nature of this mechanism, it doesn't need to just do one substitution. It could do two or more substitutions on the same molecule. So I could also take ethane and I could add some bromine to it. And if I add more bromine, this time I could get 1,2-dibromo. So both the carbons have had one of their hydrogens replaced with a bromine atom, and I get 2 hydrogen bromides. And that's one of the drawbacks of this mechanism. You can't stop it doing multiple substitutions. So we're now going to look in a little bit more detail about the mechanism for this reaction. Now you need to know that this is a free radical substitution mechanism. So the type of mechanism, it's a substitution, and it's using a free radical to do that reaction. So the first step of this reaction is called the initiation step, and this is why we need the UV light. The UV light can break a chlorine molecule into 2 highly reactive chlorine atoms. Now these chlorine atoms are called free radicals. The reason they are called free radicals is they have this single unpaired electron, and that's what we mean by a free radical, a species with an unpaired electron. So if we look at the dot cross diagram of the chlorine molecules and the 2 chlorine atom it represents. So here is my chlorine molecule. It's got a single covalent bond between the 2 chlorine atoms. The UV light can actually split that, can break that bond to produce 2 chlorine free radicals. They're free radicals because they've both got this single unpaired electron. And this is a type of homolytic fission. So we're breaking the molecule up, that's lytic, and producing 2 of the same species. So it's a homolytic fission. We come across another one later on called heterolytic fission, where we break the molecule up to form 2 different species. And we are doing a free radical substitution mechanism. So as we said, the first step for this reaction is the initiation step, where we're breaking up my chlorine molecule using UV light to produce 2 chlorine free radicals. Now we show that it's a free radical by having a single dot here. This represents my unpaired electron. The next step is what we call the propagation steps. Here we have our molecule of our alkane and our free radical. They're going to react together to form a new molecule and a new free radical. So here I've got my methane molecule with my chlorine free radical. This chlorine free radical is so reactive it's able to break the carbon-hydrogen bond. It's the only species which is going to be reactive enough to do that. So it's going to be able to pull this hydrogen away from the carbon, making my HCl molecule. That leaves behind a methyl free radical. This group now is the one with the dot. This methyl free radical is now again a highly reactive species. It's able to pull apart a chlorine molecule, and this creates the halogenalkane and regenerates this chlorine free radical. And it's important that you understand that the chlorine free radical is regenerated, not recycled or not reused. This chlorine free radical is different from the chlorine free radical we started with because it's come from a new chlorine molecule. So that's why we say that the chlorine free radical is regenerated. This is a chain reaction because now I've regenerated a chlorine free radical. It can go off and attack a new molecule of methane, and round and round and round we go until we get to a termination step. A termination step is where any two free radicals react together to form a molecule. Technically, for this reaction, there are 3 termination steps. Although this first one, the two chlorine free radicals reacting together to reform a chlorine molecule, is unlikely, as this chlorine molecule is likely to be used up in part of a propagation step. But you can get the methyl and the chlorine free radical reacting together, or, and more importantly, you can get 2 methyl free radicals reacting together. This is a very important termination step because it creates a molecule of ethane. So finding the ethane in the reaction mixture gives us the evidence that this mechanism is correct. So it's quite an interesting termination step. The problem, as we've said, with this mechanism is that it's highly unlikely it's just going to do a mono substitute. There are 4 hydrogen atoms in a methane molecule, and they can all be substituted by chlorine. So all 4 of them can be substituted. So along with chloromethane, I would also get 2 chlorine substitutions on, so that would be dichloromethane. I could also get 3, which would be trichloromethane, and last but not least, I could get tetrachloromethane. And the likelihood is I will get a mixture of the 4 different products: chloromethane, dichloro, trichloro, and tetrachloro. So this really limits this as a useful mechanism for producing chloroalkanes. So it'd be a good idea at this point to pause the video and have a go at drawing out the mechanism for the reaction of ethane with chlorine to produce chloroethane. So the initiation step is the same as before. We've taken our chlorine molecule, we've reacted it with UV light. We put the UV on the arrow because it's acting almost like a catalyst to produce our chlorine free radical. We then take our molecule of ethane, so I'm going to draw it out using displayed formula, using structural formula, but you can use displayed formula if you want to. And we've got our chlorine free radical. We're going to make HCl, and one of those carbons will have lost a hydrogen and now has a dot. I'm going to put the dot on the carbon because that technically is my free radical part. So I'm going to take this free radical now with the CH2, and I'm going to take a new molecule of chlorine, and I'm going to make my second product, which is my chloroethane, and I'm going to regenerate that chlorine free radical. Then I need to terminate the reaction. I'm going to show all 3 termination steps. So this is a possible one. If they ask you just for one termination step, I wouldn't use this one because, as I said before, it's unlikely. This chlorine here is likely to be broken up in part of the propagation steps, so you get very little chlorine gas being produced by the end of this reaction. This one is a far more common, which is my chlorine free radical and my organic or my alkyl free radical to make just the same product again, chloroethane. But an interesting one would be my two alkyl free radicals reacting together to produce a much longer chained alkane. So I've got CH3, CH2, CH2, CH3. So I've made butane, and that's a good piece of evidence that this mechanism is correct. So we're going to do this free radical substitution reaction in class, but before we do that you need to understand what hazard and risk mean and what are the differences between the two of them. So a hazard is something that could cause harm. A risk is the chance or probability that that harm will occur. Generally speaking, in chemistry, there's very little we can do about the hazard. That's to do with the nature of the chemicals themselves. We can reduce it by using small quantities or possibly by changing chemicals to something which is less hazardous. The thing we have far more control over is the risk, and we can do a risk assessment for dealing with any potentially hazardous materials. And that way we can reduce the risk that harm will occur. So we have three main ways we can reduce the risk. We can work on a smaller scale, we can use alternative techniques, and we can carry out a reaction using an alternative method that involves less hazardous substances. In this case, we're going to be working on very small scales, and any handling of the bromine will be done by the teacher in a fume cupboard. So this is our risk assessment for the reaction of hexane with bromine. And you can see there we're using three chemicals: ammonia, bromine and hexane. Of those three, bromine is probably the most dangerous, especially at the levels of concentration we need to use it. It's very toxic, it's corrosive, in other words it burns on contact, and it's dangerous to the environment. That's why it's kept in the fume cupboard, why only the teacher will be dispensing it using gloves, and any spills are very quickly dealt with and cleaned up. Hexane, generally speaking, its dangers is the fact that it is very flammable, but as we're not using any naked flames, that significantly reduces the risk. Concentrated ammonia, again, is very corrosive and dangerous to the environment, but as we're only using the ammonia vapour at very low concentrations, again, that's reducing the risk. So in the practical you're going to do, we're just going to add a few drops of bromine to our solution of hexane. Do remember this is bromine liquid, not bromine water, and that's why it's a much darker colour. So the tube in the light will decolorize, producing steamy fumes and white smoke with ammonia. The tube in the dark, there will be no colour change. The reason there is no colour change in the tube in the dark is we need the UV light to initiate the reaction. The ammonia gas reacts with any steamy fumes of hydrogen bromide to give the white smoke of ammonium bromide. Again, we have the same problem that we usually do with this mechanism. Any or all of the hydrogen atoms can be substituted for by a bromine atom. And because this is a very large alkane molecule with many hydrogens, we get a huge range of possible organic products. We've asked you to draw 3 of them, but obviously there are many, many more than 3 that are possible. We've just selected 3 at the bottom, but you could get obviously a huge number more. You could get, for example, 1,2-dibromo, 1,3-dibromo, 1,2,3-tribromo, and so on. Again, this just illustrates how useless this is at producing a given halogenoalkane. So that just finishes this video looking at the last section of the alkanes notes. In the next video in this series, we're going to be looking at the alkenes and polymers pack. So until next time, take care, stay safe, bye bye.